Hello everyone, I am Bradley Sward, Associate Professor of Computer and Information Science at the College of DuPage in Glen Ellyn, Illinois. And this video today is basically the final homework assignment for the Advanced C++ Programming course. So this is the Yahtzee dice determination problem. And so this would be easier to do if we didn't have to worry about the set and the map, but I kind of set these constraints for you just so you can kind of think in those kind of regards. So I'm going to set up a map, and I'm going to set a map of int to int. Oops, int to int, and I'll just call it M, and then I'll set up a set of integers as well, and I'll call that S. So those are my two data structures here, and set std colon. Okay, so I got my map and my set, and I'm going to do something 5 times over. What am I going to do? Of course, I am going to ask the user for the dice rolls. So I'm going to see out enter die roll, and I'm not going to worry again. I'm not going to worry about the data validation. That was your worry, not mine necessarily. That's something we cover in CIS2541. How to do a while loop to kind of make sure that the user enters the correct values. So I'm going to go ahead and set up an int for the value, and I'm into that. And then I'm going to place these things into a map. So and the set. So what I'm going to do is I'm going to insert into this guy. I'm going to take the value, pop it in. And remember that the set keeps track of unique values. So if I enter the same value over and over and over again, the set is only going to maintain one value, whatever, it's going to be that one value that gets inserted every time. So just because I insert doesn't mean I'm actually ending up inserting a whole new element. I might be just keeping the set the same based on the value I sent in. And so what I also want to do is say ++m at the value level. So I can do this because by default, if I try to access this guy and it doesn't exist in the map yet, it creates it and sets it equal to 0. So that means that whatever the map will get set with whatever die value, and this is meant to keep track of each die value that's been rolled, and that's what same as the set, but then the map will also maintain how many times that die has been rolled. So that's what we're going for here. So you can kind of see here, I'll put a breakpoint in here so you can kind of see what I'm talking about here. Run this. Okay, die roll 1, 2, 1, 1, 2. So the set size should be 2 because, and there's my 1 and my 2 because those are the 2 unique values that I input for the 5 values. And then for the map, there should be 2 elements. The size should be 2, and there should be 3 1s and 2 2s. So yes, there's 3 1s and 2 2s. So yes, so this seems to be working. So I have my die values. I have everything in the 2 data structures, and I probably don't even need the set now that I think about it, because we could probably get the same value out of this. See out. Let's just prove it, and then we can kind of even get rid of the set if we wanted to. M.size. And then print a space, and then print s.size. Excuse me. One, two, 1, 2, 1, and then yes. So yeah, the size is going to be the same for both because there are 2 elements that are maintained. There's a pair here that is, the number, the value of the die roll and how many times it's been rolled, and then the set. So actually, yeah, we can do it all with just a map. Let's just go ahead and do that. Let's not worry about anything else. Okay, so now we need to worry about everything else. So let's do that. Okay, so this is the chart that matters, and I gave you guys a link to this thing when we first started. And as you can see here, there's, based on the size, the number of elements that end up in the map, we can make distinctions, down to a pretty granular level, not all the way down. So for this, if the size of the map is a 1, we've got a Yahtzee. So if, that's pretty simple. Or I could use, if m dot size equals 1. And then that's simple. I'll just print out Yahtzee. So excited for you. Good job, you. Okay, and then that's it for that. But else if, now we say we're going to keep working our way toward this. If the size is 2, well then what happens here? You can see this is the only thing that can occur when the size of the map is 1. When the size of the map is 2, it can either be a 4 of a kind or it can be a full house. Those are the only two things it can be. You can see that because otherwise every other combination, doesn't matter what the numbers specifically are, but in this case you can go ahead and say, oh, this is cool because there's only 2 different numbers inside of here. Okay, so what's the differential? The differential is basically just to check to see, let's just look at the first element of the map, and for whatever die was rolled, if it was rolled 1 time or 4 times, then it's the 4 of a kind. And if it's not one of those 2 things, then it has to be the 2 or the 3, and in that case, then it's the full house. Okay, so to make this work then, I'm good. Since I have a size of 2, I don't have to worry. I can just go right to the begin iterator, and I can say, give me the second. Because the first will be the die value, and I don't really care about the die value itself. I just care about how many times it's been rolled. So I'll just call it x here. Int x equals m to begin second, and I can just say if x equals, I can do this 2 times over, if x equals 1, or if x equals 4, then I can go ahead and print out full house. I'm sorry, 4 of a kind. Not as exciting, so you don't get as many exclamation points, but otherwise, oh, too many curly braces. Don't you hate them? I hate them. 4 of a kind, and then this is going to end up being full house. And again, it can only be one of those 2 things in this situation. Let's try it out. Okay, so let's have 1, 1, 1, 1, 1, 1, Yahtzee. Okay, and so now 1, 2, 1, 1, 1, 1, 4 of a kind. And then you get 1, 2, 1, 2, and 2, and you get full house. And so we can do more testing on this, but this is pretty much the way to go. And so now the first 3 of these guys are solved. So the next step now is if it's 3, now it can be one of 2 things. So it's either going to be the 3 of a kind or it's going to be nothing according to our rules. This is not nothing, this is 2 pair, but in essence we don't really care about that. If it's not 3 of a kind, then to us it's nothing. Like that's just what we're going to write out. And you could easily just change the nothing to 2 pair. And I guess maybe I will, just to kind of keep consistent. And then it's only in these last 2 situations where we're going to worry about the straights. So I could do things, so else if m dot size equals 3, then we're going to do stuff. And so let's think about what that entails. How are we going to figure this out? And then I'll divvy it up here in a couple seconds. So as you can tell, there's probably quite a few ways to do this, but one way I can think of, there's a couple ways I was thinking, but in the moment right now, I'm like, well, how about we add up all the numbers of dice that are either pairs or triples, like 3 of a kind or 2 of a kind. And so we can go through, there's 3 elements, go through all 3 elements, and if the number of dice that are that specific roll are greater than 1, sum them up. So this will sum up to 3 because this 3 here, this is greater than 1, or in this case 2 plus 2. So if I go through all of these and I get a 3, then I know it's a 3 of a kind. And if I go through all of this and I get a 4, then I know it's the 2 pair. So that's what I'm thinking of here. So I can use range-based for loop, and I can just say, I'll say total or something equals 0. And I'll use my range-based for loop for every pair, let's see, for every std pair int, let me use a const pair reference for every, pair, say die roll, or just say, I'll just call it die in M, do stuff. That can help me out. Okay, so then if die.second is greater than 1, then what I will do is I'll say total plus equals die.second. Because if I just blindly add them up, yeah, I'll get 5 each time, and that doesn't help us in the slightest bit. So let me just make sure this compiles, because I could very easily have screwed up the syntax or talked myself into something else here. So far, so good. Yep, no warnings, no errors. And so this is where I could say if my die dot, oops, no, yeah. So this is where I come out of the for loop and I say if my total equals 3, then I'll print out 3 of a kind, 1 exclamation point. Else I have my 2 pair. No exclamation point, no period. That's not exciting. Let's try it out. That should do it. So let's see, 3 of a kind. 1, 2, 1, 1, 3. 3 of a kind. No, because again, if it was a Yahtzee or 4 of a kind or even the full house, that would have already been found out. And now, if we fall through all of that and we have a pair size or a size of 3 for the number of elements, it's got to be one of these two. So let's try out the 2 pair. 1, 2, 1, 2, 3. 2 pair. And you could test this out. Theoretically, I would test this out for every possibility. There's 7,776 possibilities for 5 6-sided dice, and we go from there. But I think that will do it. Go through each element. If the number of die rolls of that number is greater than 1, sum them up. You get 3. You got this guy. You get 4. You get this guy. Okay, so now it gets a little trickier here because the only thing left here when we get down to these, you have to have at least 4 to have a small straight, and you have to have 5 to have a large straight. So between these 2 cases, it's going to take a little more work to be able to figure out small straights from large straights. So let's talk about it. Okay, so let's nail out the easier of the 2 first. Maybe it doesn't seem easier because for this one here, we could have a small straight or we could have nothing. Because like if A, B, C, and D are 1, 2, 3, and 4, we have a small straight. But it could very well be where A is 1 and this is like 3, 4, 5, which means we have a nothing. So this one, there's only basically 2 ways we go: small straight or nothing. And this one here, as much as it looks more complicated, because it could be a small straight, it could be a large straight, or it could be nothing, because it could be 1, 2, 4, 5, 6, which is nothing for both anything. It looks harder, or it looks like it's going to be more challenging, but it actually is quite a bit easier. So what I'm going to do here is just set up the 4 case and leave it blank for now. And then I'm going to set up the 5 case. And so let's discuss what happens here, why we need to worry about this, and how we can differentiate between all 3 of these things rather easily. So my question is, how many different ways can you have 5 different dice when you roll them? And so take a second, think it out before I give you the answer. I'm not going to just yell out the answer. You're like, well, think it, right? Like there's 6 different possibilities of dice. And there's 6 different ways a die can be rolled, and there's this, that, whatever. And just think it out. Like there's what if it was 1, 2, 3, 4, 5? Okay, and what is missing out of this? There's only 6. So no matter what, there's going to be a number, there's going to be 5 different values out of the 6. So that means that no matter what, there's always going to be one of the die values are going to be missing. So that means there's only 6 different possible ways this can occur. something like that, where the 1 is missing. So I kind of went out of order here, but you kind of get my point here. So 1, 2, 3, 4, and 6 means the 5 is missing. 1, 2, 3, sorry for going out of order here. 1, 2, 3, 5, 6 is where the 4 is missing. How about the 3 being missing? 1, 2, 4, 5, 6. 3 is, and then the 2. And then 1, 3, 4, 5, 6. So that's it. These are the only 6 different possible things that can come up. And of course, the numbers could be out of order, or the way the map structure works, of course, is that everything will be in numerical order, low to high, right? Because that's how it organizes data under the hood. But then now, just curiousness, what is the sum of all these values? 15, 20, 16, 17, 18, 19. There's a distinct different number for each one of these 6 different cases that can pop up. 15, so the value can be 15, 16, 17, 18, 19, or 20. And so now the question is, what do we get out of this? This is a large straight right here. Oh boy, come on, text. We'll center this at least. So this is a large straight with the 15. 1, 2, 3, 4, 5. And this one is 2, 3, 4, 5, 6. That's also a large straight. And what about this? 1, 2, 3, 4, 6. That's a small straight. And what about this? 1, 2, 3, 5, 6. That's nothing. And what about 1, 2, 4, 5, 6? That's nothing. Is it? Yeah, it's nothing. And then what about 1, 3, 4, 5, 6? That's a small straight because I got the 3, 4, 5, 6. So as you can see here, as much as it seemed very complicated a minute ago, if I sum up the total of the 5 dice and I get either 15 or 20, I've got myself a largie. If I got myself 16 or 19, I have myself a smallie. And if I get 17 or 18, I got nothing at all. So let's just implement that, and we are done with the 5er for the number of sizes, and then we can work our way back. And it's a little more complicated, but not overly so. Alrighty, so to make this work, we can kind of borrow from here, right? But this time around, instead of taking the second value of how many specific values there are for a certain die roll, we take the first, because we're taking the actual results of the die roll itself, not how many dice have been rolled of that specific number. So for something like this, start from 0, take every die, now take the first value instead of the second. So as we were saying here, if total equals, double this up here, if total is equal to 15, or total is equal to 20, then I can print out large straight. Hey, I spelled it right. All right, excellent. And then I can borrow this and say else if the values were 16 or 19, then it's a smallie. Nope, there goes my streak. And if otherwise, then we're gonna print out, you got nothing. Oops, you got nothings. Watching too many kids' movies. Okay, so let's try that out. Do I get it right? Okay. Oops, sorry, I've got my homework down here underneath here. This is what that is. Sorry about that. Let's see, die roll. So 1, 2, 3, 4, and 5. I got a large straight. I got 1, 2, 3, 4, and 6. Small straight. I've got, just 1, 2, 4, 5, 6. It's got nothing. So, we're going to test this out a little bit more in a couple minutes just to make, like, how can we guarantee we have all the things we're supposed to have? We're going to test that out in a couple minutes. But for right now, we're like, oh, things seem to be working, at least on the 5 set. Okay, so now thinking about this, again, this is a little more complicated. You've got, when you have 4 die instead of 5, and we discussed earlier, you can only have a small straight or nothing. So there's no possible way to get a large straight because you have to have a size of 5. So how do we work this down? And so the first question is, how many different ways can this be arranged? How many different values can there be for the 4 different dice? And so for this, we kind of worked it out, and we did it by hand. But mathematically speaking, using discrete math and combinatorials and permutations and those kind of things like that, this was 6 choose 5. Say we have 6 choices here, and let's choose 5, and 6 choose 5 gets us the value 6. That's how we did this. So what happens if we're doing 6 choose 4? Take away the first die. There's like 4 different values. How many different ways can I take of 6 different values, choose 4 of them? And it turns out the answer is 15. And so here are the 15 ways of doing things. And these are all in numerical order, at least left to right for each individual one of the 15 ways, because that's how the map would set things up. So you can see here are the 15 different ways. Here are the sums you get if you sum up all their values. And from that, there's basically only 3 ways you can get a small straight. You get a 1, 2, 3, 4, or you get a 2, 3, 4, 5, or you get a 3, 4, 5, 6. And now you can see here, you're like, oh, goodness, okay, so what do I care about? So the same thing applies. I can steal this and just get all the die values, and then say here, if the value is 10 or the value is 18, then I have a small straight. So let's see, if the total comes out to 10 or the total comes out to 18, I have myself a small straight. Oops, move that over. And then else if, let me just put this here, else if the total is 14, that's not the end all be all, obviously not, right? Let me just, and then if it's none of those, then I have nothing, and I can go down here and steal that so I don't have to type it out. So there you go. So now if you have 14, there's how many different ways can there be 14? There's this one, there's this one, and there's this one. And so now what's the differential there? The differential for this is the small straights with a sum of 14 is the one whose first element is a 2. Basically, that's all there is to it, right? So else if, or I guess you don't really need an else if here. Oh, maybe we can figure this out. So if the total is 14, and we go in here, and we say if, and I've done this before. I could borrow this from, where am I borrowing it from? Here. I say, get me the first element of my set, of my map, and then get me that first element, but then get me the die value itself. Now I don't care how many of them have been rolled. I care what the die value is, and if that value is a 2, because that's the differential here, right? The sum is 14, but the first element is 2 for the one that's the small straight versus these other ones. And if it's a 2, then I can print. And I say this might not be as efficient as possible here, but you kind of get the point. If it's a 2, you get a small straight. Otherwise, you have nothing. So let's try it out. Okay, so let's see. 1, 2, 3, 4, 6. Oops, I'm sorry. That's not. I have to have a pair here. I have to have at least a pair here. So 1, 1, 2, 3, 4. Small straight. 1, 1, 2, 3, 5, or 54. I guess that doesn't prove anything. Again, I didn't spend the time. So there, you have nothing. And so right now, again, we're right back where we are, where we're like, can we trust this? And the answer right now in the moment is not really. As much as we've written the code and we've tested it, we go, well, how do we make this better? And coming back to here, we have all these possibilities. Our first step is not taking into account like the small straights and the large straights, is just to see, can we get the results we're looking for? Can I get 6 out of 7,766 for this, and so forth and so on? And so let me show you how we can start the testing process, finish this up. This is definitely not part of your homework assignment, but I just wanted to show you, like, if you wanted to make sure you did all the math right, how could we go about doing it? Okay, so here is the code now. I've replaced the input code from earlier, and now this code here that's highlighted, this is code that will give you all the values, because there's 7,776 different possible ways that the numbers can be rolled, 1 through 6 for each of the 5 dice. And so this goes ahead and basically sets up the map structure for every one of those possible values. And so I can run this and you can see this. Here it goes. And you can see all of them print out all the way up to 66666. I gotta watch how I say that. 66666. And then it starts at 11111. 1111. Yeah, I gotta make sure I say all the numbers right. And everything in between. And basically by treating each of these values as a base 6, which you guys should remember from recursion. I don't know why my wife is rearranging my furniture right now upstairs. But from there, now the map, each time through here, if I wanted, like the map structure holds all the 7,000 values. So now, that said, I don't need to print anything out anymore. Let's see. Let's get rid of all of this. We know it's working. So here I can replace here, I can move all of this stuff in here inside the loop. Here we go. Tab it over and add a curly brace. And so now, let's see what happens. I don't know what's going to happen, actually. Let's see what happens. So there we go. That's exactly what I expected. I'm just kidding. Of course I was expecting a little more than this. There's Yahtzee, full house, 2 pair, small straight, large straight. And I'll have to figure out what's going on. I don't know why it's stopping now, like it didn't stop before. So now, with that said, I'm going to take a look and I'll get right back to you. Yes, of course. What do I have to do here? The one thing I'm not doing is starting the map structure over every time I come around. So I'm just increasing. And of course, things aren't going to work right because the values are changing more than they should for everything else we do. And there we go. So now we have a ton of things printing out. Like we expected, there's going to be 7,776 different things printing out because no matter what happens, something prints out, right? If else, yeah, if else, yep, everything's going to print something no matter what. So now it's just a matter of going in here before the for loops and setting up some values for Yahtzee equals 0, full house equals 0, int for kind equals 0. So that this covers the map size of 1. That covers map set of 2. And right now I'm just gonna match up with this, and then we'll come back around and figure out the straights in a couple, because this doesn't account for any of the straights. So let's see. 3 kind equals 0. So we got 1, 2, 3, 4. 3 kind. 2 pair equals 0. And then 1 pair. 1 pair equals 0. And then basically nothing, if you want to think of it that way. And then we're also going to maintain the small, I'll just call it small for small straight and large for large straight. Larger, large. Okay, so we have all of these things. And I'm going to replace the print statements with essentially the things we need to increase. So I'm going to say, okay, plus Yahtzee. I just have to spell it right. There we go. And so here, this gets a plus for kind. This gets plus full house. Okay, so now 3 kind here, plus 3 kind. This is plus 2 pair. So down here is, okay, so here, if I get into here, let's see, if the size is 4, then we're here, and then we have basically just a 1 pair. So no matter what here, I'll just do 1 pair. But here, small straight, I'll just do plus small. And then here, I go plus small. And then I don't have to increase anything here because I have nothing is already accounted for up here, because, you know, remember that we did 1 pair, but we just kind of said it was nothing. So, or maybe it is nothing, but we'll see. I've never actually done this like this before, so we're just going to try it out. And if we get to a size 5, we're just going to say plus up. What did I call it? Did I call it nothing? Yeah. And then here I'll do a plus large, and then a plus small, and then nothing. I guess we could just replace it with a semicolon and just get rid of it. We don't need, and I'm not going to worry. I would get, I guess I can get rid of it. Because if it's nothing, I should not have to account for it. You never want to write code that does nothing. That's just not something you want to do. Okay, so that said, I have no idea what's going to happen. So let me run this. I don't need to print everything out. Okay, so I hit this guy here, and we have Yahtzees. We've got 6 Yahtzees. Remember to look over here while I'm doing it. We got 6 Yahtzees. We've got 300 full houses. I have it in the wrong order. There's my full house. So full house is 300. 4 of a kind is 150. 3 kind should be 1,200. 2 pair is 1,800. 1 pair is 3,600. And nothing is 720. So yes, all of these things are working out like we expected to. So at that high level, we've worked out all of these. And then the final step here is, out of everything we're doing, where are the small straights? Where are the large straights? I don't remember if it's in here per se, but I'll look it up here in a second, and I'll get back to you so we can see that we get 960 for small straights and 240 for large straights, and we'll see if that's the value that we're supposed to be getting. Okay, so let's see. I found a website for this, and I go, what are the probability of a small straight on a single roll? Technically, it's easier just to find it this way, just presuming it's a single roll, because just to come up. But if you do things the way it says, then you get 960 ways of getting the small straight, and you do the same with the large straight, and you get 240s. And that's exactly what we get, right? We get 960 for the small straight and 240 for the large. It makes sense. The large straight is harder to achieve than the small straight, so the probability right off the bat isn't very big. So, but anyway, what is that? What is this? 70 is 1%. So about 4% for a large straight, and about 13% or so, 13, 14, 15% for the small straight. Okay, so that again, I just wanted to show you guys that all of this math and all the logic that we worked out is correct. And we did everything here. I know I got rid of quite a few of the curly braces, but we got the job done in less than 100 lines of code. So some of you guys, depending on your solutions, if you're coming up with hundreds and hundreds and hundreds and hundreds and hundreds of lines of code to solve this, then you need to reevaluate your algorithm to solve this problem. So that covers everything. If you have any questions, concerns, if I misspoke anything at all like that, as always, please comment below or email me at swardb@cod.edu. So this is the last homework of the semester. The only thing left to do now is the final exam. For those of you in my class, good luck on that. And please let me know if you have any questions before the exam period starts. And have a great break. And I hope to see you guys, anyone who's listening, anyone who's watching, I hope to see you guys in other videos, or hopefully one day in person. One day over at the College of DuPage. So take care, everybody. See you in the next video. See you in person. See you online. See you around. Take care. Bye-bye.